Hello. This lecture will cover pages 105 through 108 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on additional analysis techniques, Chapter 5C, Thevenin's Theorem. If you remember when we started this chapter, we said we would discuss 5 analysis techniques. We've already discussed linearity, superposition, and now we're going to take a look at Thevenin's theorem. Succeeding lectures will talk about Norton's theorem and maximum power transfer to complete the chapter, but let's take a look at page 105, Thevenin's theorem. Thevenin's theorem states that any two-terminal linear bilateral network can be replaced by an equivalent circuit comprising of an EMF equal to the open circuit voltage of the original circuit in series with the resistance or impedance measured back into the original circuit with the load removed. We're going to go ahead and discuss this in general, and then I'm going to show you a couple problems. Thevenin's theorem is a very powerful analytical technique. And again, you'll use it many times in your courses in the future. The equivalent circuit for a Thevenin circuit looks like this. It has a Thevenin EMF and it has a Thevenin resistance. This is the only form of the Thevenin equivalent circuit. You don't have this Thevenin voltage up here, you don't have it down here. When I asked for a Thevenin equivalent circuit, it has to look like this to get full credit. How does a Thevenin circuit help us? Well, basically what it allows you to do is take any circuit or a portion of a circuit, remove a component, either one component or more components, and replace everything, in this case, in this dotted rectangle, with this circuit up here. And then you take this resistor and you place it back on. It makes the circuit analysis for additional values of RL or additional analysis purposes a lot simpler. So you could take a complicated circuit like this one, take the load resistor, remove it, mark the terminals. We'll mark the terminals A and B where we removed the load resistor or the load components. There might be more than one. And then you measure that open circuit voltage and you look back into the circuit and you get the resistance and you place them here and here. Then you put this value of RL back on, and then you can change values of RL to 1K, 10K, 100K, and make simple calculations of current and voltage. And you'll see maximum power transfer as well coming up. So if you take a look, you don't have to turn there in the book, but I want to show you the power of Thevenin's theorem. These are going to be homework problems. Some of the problems we're going to work out. Some of them will be homework. But if you look here, in this problem up here, 529, let's get this so you can see it. Problem 529 here says we want to find an equivalent circuit for V out. In other words, we're going to take this 2K ohm resistor here, we're going to treat it as a load resistor. We're going to remove it, and we're going to look back into this circuit, and we're going to simplify it down to something that looks like this. Then once we do that, we can put this 2K resistor back onto the circuit and make simple calculations for voltage out or current. How about this one down here? They want you to find I/O. Find I/O using Thevenin's theorem down here. Well, you're going to see in a minute what we're going to do is we're going to remove that resistor, label the terminals. We're going to find the Thevenin equivalent circuit for all this. Get it down to look like this with just a Thevenin open circuit voltage and the Thevenin resistance. And then on the end here, we're going to go ahead on the terminals. We're going to put that 2K back on. And I think you'll see that if you know the value of E Thevenin and you know the value of R Thevenin, and you put that resistor back on, you can calculate I/O, the current through that resistor, simple series circuit, very easily. How about down here? They want you to find V out using Thevenin's theorem. So you're going to remove this resistor. That makes this the load resistor. Just like this IO made that the load resistor. You're going to remove that resistor, mark the terminals, look back in, find the Thevenin resistance, calculate that open circuit voltage, put it back in this form right here. Once you get this form and you've calculated the Thevenin open circuit voltage and the Thevenin resistance, you're just going to place that 2K resistor back on and make the calculation for VO, which will simply be a voltage divider once you get RL on here. It's going to be E Thevenin times that resistance divided by the sum of these two resistances. I could show you numerous other problems in this chapter with independent sources and with dependent sources that you're going to use Thevenin's theorem on. But we have to discuss it and work some additional problems for you to get to where I want you to be. So here's the procedure. On page number 106, I put together a procedure for reducing a circuit to its Thevenin equivalent. The first thing I want you to do is remove the external elements. It's either one element, one resistor, in some cases it'll be multiple elements, resistors and maybe sources of EMF. And then I want you to mark the terminals A and B. You're going to see that in all three of these examples I give you. Then you're going to calculate R Thevenin by looking back into the network with all the sources set to 0. Well, you know how to do that. You just look back into the network and you reduce all the sources to 0. Voltage sources get shorted and current sources get open, all at the same time. Then you determine E Thevenin by calculating the open circuit terminal voltage between the terminals A and B that you marked up here. By any method you've learned in chapters 2, 3, or 4, reach into your toolbox, pull out loop analysis, pull out nodal analysis, pull out superposition, just use common sense with Ohm's law, and you calculate that open circuit voltage. That open circuit voltage you calculate is going to be that Thevenin voltage. By the time you get through step 3, you'll have your Thevenin voltage, you'll have your Thevenin resistance, and you redraw the circuit. So you redraw this circuit, the Thevenin equivalent, with the Thevenin voltage here and with the Thevenin resistance here, and then you place your external elements that you removed in step 1 back on here, and you make your analysis. And I think you'll see, once you do that, you can make changes to these loads very quickly and calculate currents and voltages and powers. You don't have to go back to the original circuit, which could be very complicated for each particular problem of resistance, load resistance. So here's an example. Find the Thevenin equivalent circuit for the load resistor RL below. I started out pretty simple. I want you to notice it has a voltage source here and has a voltage source there. You're going to find the Thevenin equivalent circuit for that load resistor, and then you're going to tell me what that current would be through the load resistor for RL equals 0 ohms, RL equals 50 ohms, and RL you could pick whatever, 1K, 10K, whatever. Very easy, simple series problem after that. The answer's on the next page, but before you turn to the next page, let me show you how you work this problem. First thing I did is drew the circuit, and I removed the external element or elements. So rather than redrawing the circuit, I detached this load resistor right here because I want to find IL, and IL was through that load resistor. So I removed the load and I marked the terminals. I'm going to mark the terminals A and I'm going to mark the terminals B, and that's what you'll do. Now I want to do step 2. I want you to calculate the R Thevenin resistance by looking back into the network with all the sources set to 0. Well, I'm going to look back in here. I'm going to look in from this end right here, and I'm going to see what resistance does this load resistor see when you remove it, looking back in this direction. I don't care if you start over here, or I don't care if you start here looking in. Some students like to work here and work to the left. Some students like to look at the right and work they like to start to the left and work to the right, or they like to start here on the right and work to the left. But one thing you have to do is reduce the sources to 0. That's a voltage source, you short it. I'm not going to redraw the circuit. I think you can picture that being shorted. short this one. Looking back in, do you see what our Thevenin is going to be equal to? Let's first of all start from this end, because some students may want to start from this end. It's going to be 10K plus 20 or 10 ohms in parallel with 20 in the 45. Let me say that again, because I didn't say that right. It's going to be this 10 ohms in series with the parallel combination 20 ohms and 45 ohms. Don't forget, this is a short, so these two are in parallel. So I wrote it 10 ohms plus the quantity 20 in parallel with 45, and you get 23.85 ohms. That's your Thevenin resistance. Let me try it the other way. Some students say short that, and let's look over here and start working this way. You have the 20 in parallel with the 45, so you have that quantity listed first, and then you just simply add on the 10 because it's in series with the parallel combination here. Either way, you get 23.85 ohms. That's important. On an exam or a quiz, that's worth credit. So I put a rectangle around that. Down here, I want to calculate the open circuit voltage next. Where I'm at is determine E Thevenin by calculating the open circuit terminal voltage that you marked A and B. Any method you want to use. Well, this resistor isn't here. I want to find that open circuit voltage for this circuit. I have two methods. I use the common sense method and I use superposition. I don't care which one you choose. You may want to do loop analysis. You may want to do nodal analysis. Let's see how I used common sense. With that resistor moved, and sometimes you have to redraw the circuit and don't even put that resistor anywhere near it, if it clears things up for you a little better. But if I'm at this point, and that's a ground reference, 0 volts, by the time I get up to here, what's the voltage? Oh, I'm saying it's 94.23 volts. 94.23 volts. Well, how did I get that? Well, I noticed that I have 25 volts. I'm at ground reference here, so it makes this point right here plus 25 volts with respect to this point. I'm not making this a ground reference here. B is your ground reference terminal. You want to know the voltage between here and here, not this point in here. So that's a ground reference. You're up 25 volts already right here. That's how I get to 25. And then there has to be a voltage drop across this resistor. Well, there's no voltage drop across this resistor here and this resistor here because there's no current from this source here. This has no current in the circuit because it's an open circuit over here, so this is not producing any current in the circuit. That's why I can just say 25. Plus, what's the voltage at this point? Well, it's 100 times 45 divided by 20 plus 45. It's 100 times 45 divided by 65. That's this voltage here. And you say, what about the voltage drop here? There isn't one. There's no current. It's an open circuit. So basically, from this point to this point, you have 25 volts plus the portion of the 100 that's dropped across there. You get 94.23 volts. Now, if you don't see that, and you should look at it and see if you can't figure that out, look by superposition. I'm going to find the open circuit voltage, which we'll call E Thevenin prime, due to this 100 volt source by shorting this. Well, if that's shorted, it's just a voltage divider rule between this and these two. That doesn't come into play because it's an open circuit here. So it's 100 times 45 divided by the 65. That's 69.23 volts plus to minus. How about E Thevenin double prime due to the 25 volt source? You short this. This is shorted. It's not going to give you any current at this point. It's not going to give you any current here because that's shorted now. What does this do? Well, this just provides a current rise. It doesn't provide a voltage rise here. It doesn't give you any current because it's open circuit. So that's simply 25 volts. E Thevenin double prime for the 25 volt source is equal to 25 volts. So E Thevenin double prime is 25 volts. How do I get that? You have 0 here. You're up 25. There's no current. You're still up 25. There's no current. You're still up 25. You're at 25 volts here with respect to here. That's how I get that. You add these up because E Thevenin, using superposition, is E Thevenin prime plus E Thevenin double prime. and I get 94.23 volts. That's the solution. That's the solution there for that problem. Now I know Thevenin, I know Thevenin, I know the Thevenin, I know our Thevenin resistance, I know the open circuit voltage, which is Thevenin. So I can go straight to the page that you have, which is 107. There's my equivalent circuit. I put the Thevenin voltage on with the Thevenin resistance. I attach the load resistance between A and B, terminals A and B. And now I can make simple calculations. If RL is 0, that's the current. And if RL is 50, that's the current. C Learning Assessment E5.6. Let's see where I have that at. E5.6. That's this. In your book, this is it right here. They want you to use Thevenin's theorem to find V out. V out is defined between this point and this point, V out. There's your answer. Well, how do they get that answer? I want you to use the procedure. Just go back and I want you to look at page 106. Very simple 4-step procedure. Notice that I want you to find V out. That makes this the load resistor. So you remove that 4K ohm resistor. You take it out of the circuit. First thing you do is mark the terminals then. You'll mark this terminal A and B with that removed. You reduce all sources to 0, which means you short that one and you short that one. And you look back into that circuit. Looking back into that circuit, I don't care if you take the 2K in series with the parallel combination 6K and 3K, or I don't care if you take the 6K in parallel with 3K and then add on the 2K. I think you can do that in your head. 6K in parallel with 3K is 2K ohms. Plus 2K, that gives you 4K ohms. Calculate the Thevenin voltage between here and here using superposition. You get a minus 6 volts. There's your Thevenin equivalent circuit for the 4K ohm resistor. Everything to the left of my pencil right there can be reduced to this circuit here, which is Thevenin equal to a negative 6 volts and R Thevenin equal to 4K ohms. Then I put the 4K resistor on. I put this back on at the very last step, and I calculate what V out has to be. It's just a voltage divider rule. Minus 6 times 4 divided by 8. Minus 3 volts. We're going to work additional Thevenin theorem problems for homework, but I wanted to work one more here. Example number 2. I want you to find V out, the voltage out here, using Thevenin's theorem. So basically, that makes this the load resistor, because you want to find basically the voltage across the 8K resistor out here. So I'm going to remove that. So picture this being removed, and I'm going to label this as terminal A, and I'm going to label this as terminal B, and I end up with this circuit down here. Now what I have to do is find the Thevenin equivalent for this. So I can redraw this whole circuit up here just like this. Simplify it with terminals A and B. So if you take a look, I put your steps out here. Step number 1 said remove the load resistor. That's step 1. Step 2 says find R Thevenin with all the sources reduced to 0. How do you reduce this to 0? This is where you have to be careful. But it's so easy once you see it, but there's a lot of places to make some silly mistakes. That's a current source. You open that. That's an open circuit there. You short this. And I want you to, by inspection, look back in out here, and find R Thevenin. Well, what I see is these are shorted. This is shorted, that's open. I see a 3K in parallel with 6K, which is 2K. Add it to here, which is 4K, and add another 4K, gives you 8K. There's the equation. I get 8K ohms. That's important because that's half your answer down here. How do I find the open circuit voltage here? I use superposition. I reduce this to 0. How do you reduce this to 0? You open it, and I ended up with E Thevenin prime based on the 12 volt source. What does it produce out there? And then I shorted this, put this in the circuit, found E Thevenin double prime, found that open circuit voltage there. When I added them together, I got 16 volts. We worked problems like this back in chapters 2 and 3. I get 16 volts. I put it down. There's my Thevenin equivalent circuit. Step 4 says just add on the 8K. I have 16 volts for my Thevenin, which is Thevenin voltage is 16 volts, which is basically the open circuit voltage here. Open circuit voltage and Thevenin voltage are the same thing. Add on the 8K. You can see a voltage divider here. 16 times 8 divided by 16. I get 8 volts. There's 8 volts. That's the answer to this problem. Now, there is a alternative. There's an alternative to Thevenin equivalent circuits. And that alternative to Thevenin equivalent circuits is a Norton equivalent. So these are related to one another. And I'm going to talk briefly about Norton's theorem in the next lecture. That concludes this lecture.